We are first going to do an example showing the advantages of doing area adjustment when using aggregate data. We basically want to be able to modify the normal distance calculation to include the effect of demand being continuously spread out across the aggregate demand point region. So for this example, I'm going to take 3-digit zip data for North Carolina. I'm using population greater than 0, but I believe all of the data already has populations greater than 0. It's useful to do that if you have 5-digit, because those are the ones that have 0 population. And then what I'm going to do is create some cost data for a UFL problem. And I'm going to do a normal distance calculation. So I'm going to use the DISTS function, multiply times a 1.2 circuity factor. Take the demand as being people or person, and then the transportation rate will be dollars per person mile, so that my overall C matrix then will be in units of dollars. So I can create all of that data. And then the next thing is my fixed cost. I'm just going to use a value of 6,000. I'm just making up data for this problem. And then since I want fixed cost for all of my potential sites, which corresponds to the number of rows in the C matrix, I'm going to take 6,000 and replicate that value so that my resulting C matrix, a resulting K vector, has a total of 20 values of 6,000. And then I can solve this using the UFL heuristic. And when I do that, I end up with 5 new facilities. I can then plot these facilities, and this shows the location of where the 5 optimal locations are relative to the total of 20 existing 3-digit zip code aggregate data centroids. And you can see that all 5 correspond to existing 3-digit zip codes. And then to do the area adjustment, I can take from the data, the 3-digit zip data, there is land area. So I'm going to assign that to the vector A. And then I'm going to define my area adjustment function handle. And this is a function handle that has 4 input arguments. The xy1 and xy2 are the arguments that are passed to the normal distance functions. But then there are 2 additional arguments are the areas of the initial and final points, A1 and A2. And since we'll be dealing with miles, we don't need to provide that as an input argument. And then to following the formula, the circuity factor is 1.2, and then the resulting factor for the area adjustment is 0.675 times. And then here we're using the fact of compatible dimensions. So in this function handle, we're taking the A vector and then forcing this to be a column vector. So it's a n times 1. And then for the second area vector, first we're taking the column, forcing it to be a column, and then taking a transpose of that to force it to be a row vector. So it now has a 1 times m dimension. So in terms of compatible dimensions, the resulting is an n times m matrix. And then we're taking the maximum of all of the elements in that matrix and then comparing that to the original distance matrix. And then overall, we're reporting what's the maximum of these 2. So compatible dimensions makes it easy to calculate this area adjustment. So I'm going to define my D matrix, and then I can create my area adjusted cost matrix. So now I can solve the area adjustment version of this problem, and you can just compare the results right here. We have 5 facilities originally. Now we actually only have 4. And then also our total cost, which is essentially people miles plus the fixed cost component, has increased from 5.5 up to 7.2. all raised to the 10 to the fourth power. So we've actually had a total increase in cost. And the main reason is that previously we had 5 out of the 20 new facilities had 0 variable cost. So now that we've added a positive variable cost, that's increased our overall cost. And as a result of that, the UFL heuristic has reduced the number of new facilities and also located them at different locations. So if I plot those new facilities, I plotted those as Sion V's. So let me increase the scale of this a little bit, and I can zoom in a little bit, and you can see that this has the original and the new facilities at this location. This facility over here in western North Carolina is not now established. The one here in the Greensboro area now is moved a little bit north from this location to this location. The one in the Triangle area is moved just very slightly. And then the one here in Eastern Carolina stayed at the same location. So we've gone, I think, from 5 down to 4 facilities, and I think 2 of the 4 new facilities are at different locations, and only 2 of them remain at one of the original 5 locations. So quite a significant change. Again, this is magnified. If we looked at the total percentage increase in cost, it's 27%. And as we increase the number of sites from 20 to 100 to 1,000, the impact of not doing the area adjustment gets corresponding less. So, whenever you have thousands of sites, not doing an area adjustment is not going to really affect your results very much. But when you have a lesser number, it can be quite significant. The next thing we want to talk about for the remainder of this talk would be the Popco bottling example that was presented in class. And I've taken data for this problem and have put it into a spreadsheet called Popco data, and a link to this data is available on the course schedule. And there's 2 different ways of inputting the data into the spreadsheet. The first thing I'm going to do is, this is all the data from the area adjustment example. So I'm going to click on my shortcut where I clear everything. It's equivalent to just typing clear all at the command line. And this now gets rid of everything in my command window plus everything in my workspace. So it clears everything out for this example. And then one way of actually inputting is to use the XLS Read function, which is part of MATLAB, and it reads in a spreadsheet. And it's read in a spreadsheet into this variable X. And if you look at the components, this is an array of doubles. The reason is that all the data in this Popco spreadsheet is numeric data. There is no names or strings. If there were, then it would be a second output argument returned by XLS Read that had the string data in it. And then from this matrix, essentially each column of the matrix corresponds to the different data that we're interested in. To actually see what that data is, I'm going to open a window, and then here's the actual spreadsheet. So let me go ahead and open up that spreadsheet so you can see what we're actually reading in. And it's basically just one worksheet, and the first row represents the labels. And this is an example of tabular data. Tabular data is basically where you have columns of data all headed by a name for each column, and then you have each row other than the first that represents a record of data. So this is a table type data formulation for the spreadsheet. And then each row then corresponds to one of the existing 42 bottling plants. It has the latitude, longitude, demand, and then the production and procurement cost, and then the distribution cost. So that's all of the data that we'll be reading in from the spreadsheet and is in this X matrix. So the first columns, I'm going to reverse it because I read it in as latitude, longitude, and I want to make it longitude, latitude, XY instead of YX. So I'm reversing the order of the columns. So I'm reading this. I'm going to assign it to DC. So it's a 42 times 2 matrix. Then the next F with a superscript DC. I'm going to call it just lowercase f, capital DC, is the third column corresponding to the demand in tons for the product. The next set of data is the total production and procurement cost. And then finally, the total distribution cost. So that's a way of reading in the spreadsheet into an array X and then extracting from that. There's a more flexible method if your data is structured like a table, where you have a first row with column headings. In that case, MATLAB can actually read it as a table. So we can take the same spreadsheet, read it using the read table function, assign it to T, and you can see that what is actually reported is a table argument, which is a 42 by 5 table structure. So this is an example of a extended object in MATLAB. So it's not a regular array, it's actually a table object. And it displays the format for the table. So we get a nice display of all the column headings that were in our spreadsheet, along with all of the records in each row of this. We can convert it to a structure. There's a table to structure command. If we do that, then we have a 42 element structure array. Each element of that structure array then is a structure corresponding to a bottling plant. And then we can take the structure and create the same data, the DC locations. We can create the demand for each bottling plant, the total production procurement cost, and distribution cost. So two different ways of creating the same. The top is the more flexible. If we had data that was not tabular, then we'd have to do the first alternative. If we have data that we know is tabular, then we can directly use the tabular formulation. One advantage of this is there's a series of additional functions that allow operations on table data. And since the table has a structure, the MATLAB can actually utilize that since it knows what type of data it's actually dealing with. If you've used Python, then this would be equivalent to pandas or data store in the R language. So most scripting languages now have abilities to work with tabular data. It basically started with R, moved to Python, and then most recently MATLAB now has provided this table structure. So MATLAB's a little bit late to the game in terms of being able to efficiently handle tabular data. We can create a plot of the 42, and this corresponds to the same location shown on the slides. So that's the first thing, and then the next thing we want to do is step one of the procedure, where we want to calculate or estimate the fixed cost. And to do that, we're going to calculate a linear fit for the total production and procurement cost. So first, if I want to plot the results, I can create a figure. And the reason I need to do this, unlike in the case of p-plot, is I'm doing a regular plot, not a p-plot. So first I open a figure window and then plot into that window. And then SHG refers to bringing it to the front. So these are the raw plot of the total procurement cost, and then this is the total demands in tons for all 42 of the bottling plants. And then to estimate the fixed cost, I'm going to use as my X variable the demand in tons. My Y values are going to be the TCP values. And then I'm going to create a function handle to estimate, and I'm going to basically take two parameters, the intercept and the slope, and define this as a function handle, and then I can use this function handle inside of another one that becomes then just a function of the parameters. And then since it's just a function of the parameters, I can use fminsearch to minimize, in this case, the square deviation. So I'm basically doing a linear regression. And AB corresponds to alpha beta, a generic way of characterizing the intercept and slope of a linear regression fit. And then this is the result I get. And then now I want to assign them to particular values. In this case, the intercept is my fixed cost K, which is 1.06 to the 7th. And then CP represents my variable production cost. So this is the amount it costs to produce 1 ton of the bottled product produced at each of these plants. So it's about $126 per ton. And that's actually the production cost. I'm sure there's a large markup, so it would probably sell for much more than that. Okay, here I'm going to plot so you can actually see the regression fit. And when I do that, you can see this is the straight line fitted to the actual data. And where it intercepts here, just a little bit above 1, is what we're going to be using as our fixed cost. And then the 126 represents the slope of this line. And at this point, we're really going to be then essentially throwing away the variable production cost because that's not needed for our logistics network analysis for this situation. For step 2, we're going to pick 3-digit zip codes as our aggregate demand points. So I'm going to call the US zip function. All I want are 3 pieces of information from the 3-digit zips. The XY location, which I'll label as P, and then Q is going to represent the population of each 3-digit zip, and then A is going to be my area vector for each demand point, aggregate demand point. And then I'm going to exclude the I'm going to exclude any zips that are not within the continental United States by using the multiple OR function. So here I get all of those points, and if you look at it, the total number is 880. I'm going to redefine my function handle because I've deleted it from the previous example. That's just the same function handle that I used before. And then here the first step is to allocate demand to the DCs. So I'm going to be using this area adjusted distance calculation, and I'm going to then look individually at each of the 3-digit zip code regions, and for each of those determine what is the distance from that 3-digit zip centroid to all of the 42 distribution centers. And I'm going to then return what is the minimum distance, and then also what is the index corresponding to the minimum distance bottling plant. And to do the area adjustment, I'm going to pass the corresponding area for each 3-digit zip to the function handle. And then since all of the bottling plants are actual locations, they don't have any area associated with them. So the function handle works if I just pass it a 0 value. If I passed an empty value, it would not work as a function handle. So I have to explicitly say that the area is actually 0 for these points. And then when I do that inside of this loop, I'm setting the maximum distance. This is the distance for a round trip truck travel, the amount that a truck can travel within 1 day. The reason to assume round trip in this case is that the delivery vehicles are not ones that are going to then pick up another load and go somewhere else. They're typically used just for deliveries from particular bottling plants. So in this case, they're trucks that are actually typically even owned and operated by the actual bottling company. And that's the reason for the 200-mile restriction. And then I'm going to look and see if my minimum distance found is actually less than 200 miles. If so, assign the corresponding index to an index vector. So before I get into this loop, I'm first setting all my indices equal to 0. And then I'm going through the loop, sending the ones that are within the 200-mile limit to the corresponding value. And for example, like a 3-digit zip that's in North Carolina, since all of my bottling plant market area is in the West Coast, the 3-digit zip corresponding to somewhere in North Carolina would be a couple thousand miles away. So it would be well beyond this Dmax value. So none of the East Coast 3-digit zips would be included, and they would all have 0 value when I finish this loop. So now I've assigned all of the positive values that are within the 200-mile radius. And then at this point, I want to remove the unallocated points. So I'm starting off with a total of 880 demand points, but then I'm going to find the index values that remained at 0 that have not changed from their initial assignment. And for those, I'm just going to remove them from P, and then do it also for Q, for A, and then also for the index vector itself. It's important that I do this as the last step. If I did this first, then none of this would work. So I'm going to do this in this particular sequence. And when I've done that, if I look at the P matrix now, it has 161 as opposed to 880. So that's the number of active demand points. It is possible that some of the bottling plants were not chosen as being closest to any of the 3-digit zips. So in that case, their indexes would have remained at 0 and then been eliminated in this step here. So what I'm doing here is calculating the set difference between the original set of bottling plants 1 through 42, and then comparing that to how many unique indices are left. And if the set of unique indices does not include all of the starting distribution centers, that'll be returned in a second index vector called index 0. So anything other than empty would indicate that I have some unallocated. In this case, it comes back empty. So all of the bottling plants have at least one 3-digit zip allocated to it. A question, what if it did come back non-empty and there were one or more of the bottling plants that did not have any? Well, first, that would be unusual because the bottling plants are serving a retail population. So it would be odd that an actual ongoing bottling plant that's operating would be far from any population source. So in that sense, it's unlikely. Then a question would be, what happens to the demand in terms of total distribution cost that the distribution center was serving, assuming that that value is non-zero? One idea would be to maybe take that value and allocate it to all of the other distribution centers so that our total distribution cost stays the same. I think probably a better approach would be just to eliminate that part of the total distribution cost. So I would add to this change here, I would go to the TDC value for any of the index 0 values and just set those equal to the empty set so they're eliminated. So I would essentially just be ignoring that portion of my total distribution cost. Luckily in this example, this does not occur. Okay, the next step, step 3, is to allocate demand to the customers based on population. This is a pretty straightforward implementation of the procedure shown in the slide for step 3. Here, I think the only thing to really note of this is that here I'm using the fact that I can actually find, first using the argmin function, all of the distances that are minimum and are equal to I, and I'm going to assign that to determine the indices of my particular bottling plant's set of market demands. So M sub I represents the indices of all the 3-digit zips that are assigned to that bottling plant, and I can assign it to a cell array. So notice the curly brackets here. The nice thing about using a cell array is that the number of indices is going to differ for each distribution center. One might have 2 or 3, others might have 5 or 6, 7 or 8. It doesn't matter for a cell array. So we're taking advantage of that flexibility to have differing numbers of elements reporting corresponding to the different numbers of indices. And then we can immediately use that value that we've just created by then looking into the population vector and extracting those elements, dividing it by the sum of those elements, multiplying that times the demand for that bottling plant, and then assigning the population weighted proportion to each of the demands for all of those demand points. So again, this is directly implementing that step shown in the slides. It's a nice, I think, example of what you can do in MATLAB to directly match. And when we do that, the last step here is I'm using the variable display function just to see, did my allocation work as expected, in the sense that if I add up the sum of all of my bottling plant demands, the sum of the FDCs, does that value equal the sum of all of the Fs that I've created by doing this allocation? So they started off at 0, and then as a result of this allocation loop, I've done the allocation, and then when I finish, the sum of all of those should equal the total. If not, some cases this won't be exactly right, and you can see it's not because of round off error. Here it's exactly an integer because that was the original input data, but as a result of the division occurring at this step, there's some numerical inaccuracy, and that's reflected here in that the value is not exactly an integer. It probably has a positive component in the 5th or 6th decimal point to the right in this number, so it's a very slight numerical difference. Step 4 of the procedure, we're calculating the nominal transportation rate, and that's 1.77, and that's in terms of dollars per ton mile. What's important about this POPCO example is that the actual units of demand are in tons, and then all we're using the population for is to do this weighted allocation of the tons. So population then doesn't appear in any of the other subsequent pieces of information that we're creating. It's only used in this one step to do the allocation for each of the 3-digit zip regions. Step 5 is to solve the UFL problem and the 161 3-digit zip regions and appending to those 42 bottling plant locations. So now we have a total, when we do that, of 161 plus 42 of 203 potential new facility site locations. And the set of existing facility locations is just equal to the 161 three-digit demand points. The area for all of these, we're going to assume that's equal to 0. And here we're going to set the area equal to the original areas of the 3-digit demand. And again, it doesn't matter that we're assigning 0 to the p-values because we're accounting for the areas in the second argument because the same p-value is used. So with that distance calculation, then we can calculate our C matrix. And we look at it, the dimensions are 203 times 161. And then we can call the UFL procedure. And this is the hybrid UFL heuristic. When we call it, you can see this is the series of steps that occur. This is the original UFL add heuristic that constructs the solution. Then we exchange and we get a significant reduction from 139 down to 709. And then the add procedure was applied and essentially no change, nothing was added. Drop procedure was applied, none of the facilities were dropped. So at that point it finishes. So there's really just one step through the hybrid procedure. And in doing that, the number of new facilities is 23. So we've gone from 42 down to 23, just a little over half. So quite a significant reduction in the number of bottling plants. To calculate the cost, the new total distribution cost is 4.6 to the 8th. The total cost, which includes the fixed cost plus the distribution cost, is 7.09. By way of comparison, the original total distribution cost is 4.49, actually slightly lower. So we actually had an increase in distribution cost, but when we look at the total cost, we've gone from 8.9 originally down to 7.09. Quite a substantial overall reduction, mainly because we've reduced by almost half the number of new facilities required. And that's our fixed cost saving. That's quite substantial. To look at the percentages, there's been a 3.5% increase in distribution cost, but overall cost have dropped to just under 80% of what they were originally. If we want to see what our results look like, we can first define the set of potential new facility sites and then call the p-plot, where we're going to then just take the y elements. I can't do this in one line. I can't apply y to each of these separately because I first need to append both sets of locations into a new variable. Then I can apply the y variable returned by UFL, which are the indices, into that combined array. And I'm going to plot those then as green circles as opposed to the red dots, which represent the original facility locations. So you can see that there's in some cases quite substantial changes in the number of facilities. In other cases, these are, I think, at a similar location. This is a new location that's serving, the demand probably served by these 3 locations in Montana. these are at the same location, and you get a fairly significant reduction in the total spread. So as a result of this logistics analysis, we've seen a substantial change in the total cost reduction, a value of almost a 20% reduction as a result of this, reducing by almost half the number of new facilities. And then the last step I'm going to do is save all this data as a .mat file. I'm going to call it popco UFL. I'm going to save the fixed cost I calculated, my C matrix, and then I'm also going to save S, the structure corresponding to the actual structure that I created from the table data.